Plot a graph of y equals x and find the gradient and the y-intercept of the plotted graph. Let's move on to the next slide where we can see we have y equals x. Now we looked at how we could plot this in an earlier video in this playlist. Here I'm just going to let the animation run without commentary, just to remind you of how the plotting process takes place. Let's now work out the gradient of the plotted graph. And I'm going to start off with by marking a point on the graph, which I'm labeling point P. I'll now choose another point on the graph, which you can see I've labeled as point Q. Now point P is at 1 on the x-axis and point Q is at 2 on the x-axis. Now the distance between the x-axis position of P and Q is referred to as the run. On the y-axis, P is at 1 and Q is at 2. Now the distance between the P and the Q on the y-axis is referred to as the rise. To emphasize the point, I'm going to choose two different values of P and Q on the graph, and you can see that if we come along here, that's the run. That's the distance between the x-axis positions of P and Q, and this here is the rise, and that is the difference between the y values of the P and the Q. And you can think of this as you go along the run and you see how much the line actually rises as you move along. Now to calculate the slope of this straight line graph, or the gradient as it can also be called, you use the rise and the run according to the following, that the slope equals the rise divided by the run. Now if we consider the run, we start at this point and we go 1, 2, 3. So the length of the run is 3 units. Of course we can calculate the run by considering the points on the x-axis, which means we subtract from this 5 this 2, which will give us 3. If we consider the rise, we start at this point and we count 1, 2, 3. So the rise is 3. Alternatively, we could subtract this 2 from this 5 on the y-axis, because the 2 and the 5 are the coordinate positions of the P and Q along the y-axis. So we can continue and we can see that the slope is the 5 minus the 2, which is how I calculated the rise a moment ago, and the 5 minus the 2, which is the way in which I calculated the run a moment ago. And of course, we can show this to be 3 over 3, and consequently, the slope is equal to 1. So the slope of this graph is 1, and it's the same slope along the entire length. It's got equivalent steepness, if you like, all the way along the graph, because it is a straight line graph. To emphasize the point about the slope being the same throughout the entire length of the graph, I'm going to choose two different points for P and Q. This is the first point, and you can see that at x position 1 and y position 1, the coordinate position is 1, 1, and I'm going to choose Q, and you can see that at coordinate position 3, 3. Now what I'm going to do, I'm going to mark out the run, and this is 2. And now I'm going to say for that run, the graph will rise by this amount, which is 2. So we've gone 2 units on the run and 2 units on the rise. So we can work out the slope again, being the rise divided by the run. And of course, that's 3 minus 1, which is the position of the P and the Q on the y-axis. And the 3 minus 1 here was taken from the x-axis. And that will give us 2 over 2. And we can see the slope is still 1. So regardless of where we put the P and the Q, we get a slope of 1. Continuing on the next slide, you can see I've marked off a P and a Q. And if you look at the run and the rise and observe it yourself, you'll see that the slope is still 1. If you go on and move it to here, the slope will still be 1. Observe it yourself and calculate it yourself. If I move it to here, it's still a slope of 1. If I move the P and the Q further apart and we look at the run and the rise, you're still going to get a slope of 1. In other words, for every unit you move forward along the run, you rise by 1 unit. That's what a slope of 1 is really telling us here. The slope of a graph is also referred to as being the gradient of the graph. So the gradient of this graph is 1. You can also often see the gradient represented by m, such as m equals 1, where m is representing the gradient. And this m is part of the straight line equation appearing now, y equals mx plus c. Let's take a closer look at this equation. Now, we've just discussed the fact that m is the gradient, and for the graph we're looking at, we worked that out to be 1. So we can say that m is 1. So we led on now to ask the question, well, what is c? Well, we covered this in a previous video in this playlist. C is the intercept. It's where the graph crosses the y-axis. So let's have a look at where that is. And if you have a look, you can see it crosses the y-axis where y is 0. Consequently, we can see, if you look to see, that it is going to be 0. So for the graph we've plotted, we can write out the equation as shown here. Y equals 1x plus c, where 1 is the gradient and c is the intercept. Now this is an equation for a straight line graph, and this is the straight line graph here. Of course, it is possible for me to write this as shown here, because this is 1x, which is this x, and of course if I'm adding 0 to it, I've no need to show that here. Now, if you consider y equals x for a moment, this is where we came in at the beginning of the video, because you were asked to plot y equals x, and this is the slide where the plot took place. And you can see it's the graph that we've been working on throughout this video. This is the general form of an equation for a straight line graph, and you could be forgiven for thinking that this doesn't look anything like the equation for a straight line graph. But it is. It's just that m, the gradient for this, is 1, so we don't see anything in front of the x, and the intercept is 0, so there's no point putting it in. So this is an equation for a straight line graph, which we showed here at the first slide of this video, which gave us this straight line graph here, as you can see.